Hello everyone, in this video we're gonna learn recurrence relations using generating functions. So probably one of the most well-known recurrence relations will be the Fibonacci recurrence relation. So let me give the definition first. The Fibonacci number f of n is defined by the recurrence relation. The initial conditions f0 equals 1, f0 equals say 0, f1 equals 1, and for n greater than 2 we can compute this using the recurrence relation like this for n greater than or equal to 2. So example, f0 equals 0, f1 equals 1, and f2 is the sum of the two previous numbers. So 0 plus 1 is 1, so f3, 1 plus 1 equals 2, f4, 1 plus 2 equals 3, f5, 2 plus 3 equals 5, f6, 3 plus 5 equals 8, etc. In this way we can compute. Okay, and there are many interesting numbers, interesting objects which are counted by the Fibonacci number. So one of them is the following: the number of ways to write n as say ordered sum of ones and twos is equal to the Fibonacci number f n plus 1 actually. So why? So for example, 5 can be written as 1 plus 1 plus 1 plus 1 and also plus 1, and also 2 plus 1 plus 1 plus 1, or 1 plus 2 plus 1 plus 1, 1 plus, maybe it's too long, 2 plus 1, 1 plus 1 plus 1 plus 2, and also 2 plus 2 plus 1 equals 2 plus 1 plus 2, 1 plus 2 plus 2. So there are 1, 2, 3, 4, 5, 6, 7, 8 ways to write 5 as a sum of ones and twos. And notice that I expressed 5 as a sum 2 plus 1 plus 1 plus 1, and also 1 plus 2 plus 1 plus 1. They are considered to be different because we are considering ordered sums. We also take into account the order of the summands. So there are 8 possibilities. So, and this is, so 8 is equal to f of 6. So this is this confirms that this sentence is true when n equals 5. And we can prove this using induction. So the proof of this, suppose that is true for n. So n is greater than equal to 1. And for n plus 1 case, for the n plus 1 case, when we want to write n plus 1 as a sum of ones and twos, then the first summand could be 1 plus something, or 2 plus something. But here we need to write, it's a sum of n using ones and twos. And here, because we used 2, we should be write n minus 1 using 1s and 2s. And this number will give us f n minus n plus 1. This number will be f of n. And because the sum of these two, okay, let me go back. The number of ways to write n plus 1 as a sum of 1s and 2s is equal to f n plus 1 plus f of n, and because it is Fibonacci number is equal to f n plus 2. So this confirms that it's the case n equals n plus 1 case is also true. So by induction we are done. So this completes the proof. Here I used f n plus 1, or I used the same notation. Alright, so we know this Fibonacci number, but it has a nice and simple recurrence relation. But our goal is to find an explicit formula for the nth term without referring to the previous terms. So the goal, the question, can we write down a formula for f of n, f sub n, without using recurrence relation. And we're gonna do this. We will do this using generating functions. So let's find the generating function for the Fibonacci number. Alright. So method, generating function. So let f of x to be the generating function for the Fibonacci number. Okay. So it's gonna be f sub 0, f sub 1, x, f sub 2, x squared plus dot dot dot. And we will write this. We will find the functional equation for this generating function capital F using the recurrence relation. So f0 equals 0, so we can, this is the same as, okay, and this is 1, so it's x and plus things like that. So I'm gonna separate them. Alright, I'm gonna write this way. So 0 plus x plus, and then n goes from 2 to infinity fn x to the n, because we're gonna use this recurrence relation, and this is valid when n is greater than or equal to 2. So now from here I'm going to so this is going to be x. I'm going to substitute the recurrence relation. Then this is going to be this plus n minus 2 x squared. Okay, and now we can separate the sum. 2 to infinity fn minus 1 x squared, 2 to infinity fn minus 2 x squared. Now from here, let's for the first summand, let me replace n by n plus 1. Then n is from 1 to infinity. It's gonna be fn. Oh, I made a mistake over here. This should be our n. It's n x to the n plus 1. And in the second sum, I'm gonna change n by, replace n by n plus 2. Then n is from 0 to infinity, and it's x going to fn times xn plus 2. Alright, And this one, the first thing, we can factor x out in front. And n is from 0 to infinity, fn. And I replaced n here from 1 to n from 0, and because this is okay because f sub 0 equals 0. Plus I factor out from this second sum, I'm going to factor out x squared. And from 0 infinity fn x squared. N. Now notice that this part is f, capital F. This part is also capital F. So we obtain that this is equal to x times x f of x plus x squared f of x. Okay. So if let me write down this the next page. So what we found is that x plus x f of x plus x squared f of x. Now let me move this part, these two terms to the other side and factor the f of x. Then we get this equation, and finally we can divide both sides by 1 minus x squared. So we have this recurrence. From the recurrence relation, we found this formula for the generating function. Alright, now what are we going to do? What are we going to do here is that factor the denominator. So we can write this 1 minus x squared, like 1 minus alpha x times 1 minus beta x. We can write down this because it has solutions. And actually alpha equals 1 plus square root of 5 over 2. Beta equals 1 minus square root of 5 over 2. We can write alpha and beta. You can find alpha and beta by solving this quadratic equation. Alright. I'm gonna then f of x is equal to x over 1 minus alpha x 1 minus beta x. Now we can do partial fraction over here. So f of x is equal to 1 minus alpha x capital A over 1 minus alpha x, capital B over 1 minus beta x. We can find real numbers or complex numbers, capital A and B, satisfying this relation. Okay, how can you find such alpha and beta? We combine the two fractions, and here is going to be I times 1 minus beta x plus b times 1 minus alpha x, and we can collect the two constant terms and minus a beta minus b alpha x. Okay, this means this should be x. The numerator must be x, so that means a plus b equals 0, and alpha beta we can a beta plus b alpha must be minus 1, because here we have minus alpha, we have minus sign there. And if you solve these two equations, we know alpha and beta over here. So if you solve this, then you will get a equals 1 over square root of 5, b equals minus 1 over square root of 5. You can just solve this system of linear equations easily, and you get two solution for a and b. So what now? F of x here, if I write this again, we get 1 over square root of 5 1 minus alpha x minus 1 over 1 minus beta x. Okay? Now look at each term. This is a geometric series. You can expand this very easily. So it's 1 over square root of 5 and summation, and it's from 0 infinity alpha to the n x to the n plus, and from 0 infinity beta to the n x to the n. Okay, now we can combine this, and we can move this factor 1 over square root of 5 inside. Then what we get is this, alpha to the n minus beta to the n times x to the n. Yes, I think I made a mistake over here. It's going to be minus. So, and we know that this is the generating function for the Fibonacci number. That means f of n must be equal to this. So conclusion, thus we obtain a formula for f of n, 1 over square root of 2. Now we're gonna replace alpha with this value over here and beta for this. Then we get 1 plus square root of 5 over 2 to the n minus 1 minus square root of 5 over 2 to the n. So this is a formula for f of n. It looks a bit strange because it contains irrational number like this one and this one, but if you compute this for any natural number n, you will end up getting a natural number, which is the Fibonacci number. So this method, this example illustrates how we can find a general formula for the nth term of a recurrence relation, like a Fibonacci number. So let me summarize this in the next page. So, solving recurrence relations. So we need some definition. Okay, homogeneous linear recurrence relation is in the following form. If a recurrence relation is written in this way, it's called homogeneous and linear. For constants C1 ck. So, for instance, the Fibonacci sequence or recurrence relation. This is a homogeneous linear recurrence relation, or some recurrence relation like this. Homogeneous. Homogeneous here means that it doesn't have a term without that sequence. So here, for instance, if we had plus n something like this is called, if there is a term like this, n, or some constant, anything without a term like this is inhomogeneous. In this case, inhomogeneous. But here we're going to consider only homogeneous recurrence relation like this. And the characteristic polynomial, let's continue the definition. The characteristic polynomial of the recurrence relation, say this star, the homogeneous recurrence relation star is x to the k minus c1 x to the k minus 1 minus c2 x to the k minus 2 minus dot 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 minus ck equal. This is polynomial, the characteristic polynomial. And the theorem is if the characteristic polynomial has k distinct roots, are the k distinct roots of the characteristic polynomial of the homogeneous recurrence relation, then the solution can be written as an equals alpha 1 r1 to the n, alpha 2 r2 to the n plus dot dot dot, alpha n r or alpha k rk to the n for some constants alpha 1 dot 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 alpha k. So let's consider the let's see for the Fibonacci recurrence relation. Here Fibonacci recurrence relation is a homogeneous linear equation, and we know the characteristic polynomial. Okay, example fn minus 1, fn minus 2 Fibonacci case. The characteristic polynomial in this case is x squared minus x minus 1. So what is the solution to this? And if you say it equals 0, then x equals 1 plus minus square root of 5 over 2. So by theorem, f of n can be written as, say, alpha 1 times the root plus alpha 2 times 1 minus square root of 5 over 2 to the n. We should be able to find these two constants, and we can find this by using recurrence, by using the initial condition f1 equals 1. So because f0 equals, if you substitute n to be 0, then we get alpha 1 plus alpha 2 equals 0. And f1 equals 2 alpha 1 times 1 plus square root of 5 plus alpha 2 to 1 minus square root of 5 equals 1. If you solve these two equations for alpha and beta, you will get alpha 1 equals 1 over square root of 5, beta 1 equals minus 1 over square root of 5. This will be alpha 2. So this is the solution that we obtained earlier using generating functions, but the idea is the same. So in like this, if the characteristic polynomial has distinct roots, then you can always write down the formula used like this. Okay, this is the end of the video. Thank you.